Dear viewers, I hope you are doing well and having a great day. Today's lecture is very important. It is about the stability of equilibrium points. More precisely, today in this lecture, we shall be discussing about equilibrium points, their stability, and what these stability results mean, especially for single species exponential growth model. So if you recall, in the last lecture we discussed about the single species exponential growth model, which is given by dn over dt equal to Rn. Here R was, we have defined last time, intrinsic growth rate, and n t is the population density of the species or organism at time t. We just name this equation as equation number 1. So we will talk about the equilibrium points, their stability, and we will also discuss the ecological interpretation of the stability results for this model system 1. But before that, we shall discuss in general what is the meaning of equilibrium point of a dynamical system, their stability, and then we will come back to this model system and we will discuss the equilibrium points and the stability of this model system. So let us first talk about the equilibrium point. Before discussing this, let equilibrium points and their stability, let me tell you that I will make a separate video about these concepts of equilibrium points, their stability, asymptotic stability, global stability, unstable equilibrium point. In that video we shall discuss all these things explicitly, but here we are talking about these concepts because we have to discuss about the equilibrium points and stability of the exponential growth model system 1. So in general, let us assume that dx over dt is a dynamical system. Dx over dt equal to fx is a dynamical system. We name it as equation number 2. So an equilibrium point of this dynamical system 2, or this dynamical system may be the any biological system, or simply it is a differential equation. So by an equilibrium point of this system we mean that a state where the system does not change over time. So if we assume that x equal to x star is an equilibrium point, so just E dot means equilibrium, P dot means point, so E dot P dot means equilibrium point. So if x equal to x star is an equilibrium point of system 2, then because in the definition of equilibrium point we told that it is a state of the system which does not change over time. That means rate of change at this point, that means dx over dt at x star, that is f at x star, is 0. So in other way we can say that if a system starts at an equilibrium point x equal to x star, it stays there forever because the rate of change at x equal to x star is 0. So if the system starts at x equal to x star, it will remain there for all the time. But there is an important fact about this equilibrium point, that is an equilibrium point of the dynamical system 2 is also a special solution of the dynamical system 2. This is very interesting fact because you see x equal to x star is a constant, right? That means this is a point, so it is constant. So the derivative of this x star over t is 0. So left hand side is 0 and the right hand side we have seen that f at x star is 0. So that means x equal to x star satisfies the model system 2 or dynamical system 2. Hence x equal to x star is also a solution of the dynamical system 2. So the definition of the equilibrium point of the dynamical system 2 can be given like this also. An equilibrium point of the dynamical system 2 is a special solution of the system 2 which does not change over time. So far we have been discussing about the concept of equilibrium point of a dynamical system. Now we shall discuss about the stability of the equilibrium point of a dynamical system. So stability of an equilibrium point of dynamical system 2. Dynamical systems 2. Recall dynamical system 2. Dx over dt equal to, here I will again write dx over dt equal to fx. This is your dynamical system 2. So the question is that what do we understand about the stability of the equilibrium point x equal to x star of dynamical system 2. Simply, if we talk about the stability of the dynamical system 2, it means that what happens if the system is slightly disturbed from its equilibrium state. So what we are telling that if we slightly disturb this system 2 from its equilibrium state, then what happens about the disturbance, whether the disturbance grows or decays. This is measured by the concept of stability. So there are three important points that we are going to discuss. One is the stable equilibrium point. Stable equilibrium point, and the second is asymptotically stable equilibrium point. Asymptotically stable equilibrium point, and the third is unstable equilibrium point. Unstable equilibrium point. So we will start our discussion with first one. What do we understand by a stable equilibrium point? So suppose x equal to x star is an equilibrium point of the dynamical system 2. If the system stays close to x star after a small disturbance, then we say that x star is stable. What actually we are telling that if we make a small disturbance into x star and then even the solution of this system 2 remain close to x star for all the time t, then we say that x equal to x star is a stable equilibrium point. So in symbolic way we can write, if we are putting a small disturbance into x star, small disturbance, then it actually tells that stay close. And furthermore we can define the stability of the equilibrium point in the terms of epsilon delta definition also. Actually the equilibrium point x equal to x star is said to be stable if for every epsilon greater than 0 there exists delta greater than 0, such that mod of x at t naught minus x star is less than delta, implies mod of xt minus x star is less than epsilon for all t greater than or equal to t naught. So the xt is a solution of the dynamical system 2, and x at t naught is the t naught is the initial time, and x at t naught is the value of the solution at t equal to t naught. That means initial value of the solution at initial time t equal to t naught. So what this definition says that whenever your initial solution x at t naught is closed enough to x equal to x star, that means x equal to x at t naught is in the delta neighborhood of x star. That means if I say this is your x star and there is some delta neighborhood of x star, so this radius of this disk is delta, and here you have x at t naught, and the distance between the x and t naught is less than delta. Okay, so if your solution starts from here, then ultimately for all the time t greater than or equal to t naught, this xt can again bounded into some other disk, open disk, having the radial distance epsilon. So this definition simply says that if you start close enough to the equilibrium point x star, that means you are here at xt naught, which is in the delta neighborhood, then the system always stay close to x equal to x star. So the system means this solution xt for all the time t equal to t naught remains in the epsilon neighborhood. This is the what we have discussed is about the stable equilibrium point. Now we will come to the asymptotic stability of the equilibrium point x equal to x star of dx over dt equal to fx. Second point that we have we are going to discuss is the asymptotic stability. Asymptotic stability. Okay. If the system not only close but actually returns to x star, then we say that x equal to x star is asymptotically stable. So what actually we are telling that the equilibrium point will not be only close to the disturbance that we have created into the equilibrium point, that will not be only close to x equal to x star equilibrium point, but it returns to the equilibrium point as the time passes out. So that means a small disturbance, implies come back to the equilibrium point. So in the terms of epsilon delta definition, what we can say that an equilibrium point x equal to x star is asymptotically stable if number 1 it is stable, number 2 this limit t tends to infinity, this xt is nothing but x star. So in case of asymptotic stability, The equilibrium point x equal to x star not only stay close, but eventually returns to the equilibrium point. That means it will stay close by the point first, and it will eventually returns to the equilibrium point x star by the point 2. So if these two things happens together, then we say that the equilibrium point x star is asymptotically stable. So what is the basic difference between the asymptotic stability and stability? In case of stable equilibrium point, the disturbance remain close to the equilibrium point, while it does it actually decay out to zero in the case of asymptotic stability. So if you see, asymptotically stable equilibrium point is stable equilibrium point, but converse is not true. So what is the main result we are getting the as a relation of asymptotic stability and the stability is that asymptotically stable equilibrium point implies stable equilibrium point, but converse need not be true. That means a stable equilibrium point need not be the asymptotically stable equilibrium point. Now we'll come to the third definition. If you recall that we have mentioned, third one is the unstable equilibrium point. Unstable equilibrium point. So very simply you can say that a equilibrium point which is not stable is called the unstable equilibrium point. Or we can say that if the system moves away from x star, the equilibrium point, after a disturbance, we say x equal to x star is unstable equilibrium point. So it says that if the disturbance made in x equal to x star grows as the time passes out, then we say that x equal to x star is an unstable equilibrium point. In the terms of epsilon delta definition, what we can say that equilibrium point x equal to x star is unstable if there exists an epsilon greater than 0 such that for all delta greater than 0 we have mod of xt minus x star less than delta, but for some time t greater than or equal to t naught, the distance between xt and x star is greater than or equal to epsilon. So what is the meaning of this? It means that no matter how much closed the equilibrium point x star is with no matter how much small neighborhood delta we choose around x equal to x star. You see how much small neighborhood we choose around x equal to x star, this delta neighborhood. There is always a starting point close to x star, that is x at t naught, whose trajectory eventually leaves a fixed neighborhood epsilon, because this distance between xt for all t greater than or equal to t naught leaves the epsilon neighborhood. So in simple terms, unstable fixed point means every tiny disturbance can make the system move away from the equilibrium point. So the basic difference between the stable and unstable equilibrium point is, in case of stable equilibrium point, for every epsilon greater than 0 we can find a delta, so solution stay close. In case of unstable equilibrium point, as you are seeing here, some epsilon greater than 0 exists such that no matter how small delta we choose and your initial solution is closed enough to x star in this delta neighborhood, but solution can escape the epsilon neighborhood. So this is all about what we discussed about the equilibrium point and their stability in general. Now we shall discuss the equilibrium points and their stability in the case of exponential population growth model. So you recall that we mentioned the exponential population growth model by this equation dn over dt equal to Rn. Suppose this is equation number 1. So we have learned that at the equilibrium point the rate of change must vanish. So at the equilibrium point of this exponential growth model, the rate of change must vanish, that is dn over dt must be 0, that is Rn must be 0. So this means n equal to 0 because r is not 0 in general, and we can also denote this n by n star. So that means at n equal to n star the rate of change dn over dt vanish. So hence n equal to n star becomes the equilibrium point of the model system 1. So that means there is only one equilibrium point, n star equal to 0 is the only one equilibrium point of the model system 1, is only the equilibrium point of model system 1. Now what is the ecological sense of saying n star equal to 0 is the equilibrium point of the model system 1? As we know that when we derived this model system 1, we have assumed that there is no emigration or immigration is involved. Hence, if there is no population is coming in or no population is coming out, hence the population, if it starts at n star equal to 0, it will remain there. So this is the ecological explanation of saying n star equal to 0 is the equilibrium point of the model system 1. That means the population that starts at 0 remains or stay at 0. The population that starts at n star equal to 0 stay there at, and which satisfies the definition of the equilibrium point. Now we shall discuss the stability of this equilibrium point n star equal to 0. So we have already discussed the definition of stability in the terms of epsilon and delta, and we have also discussed the literal meaning of stability of equilibrium point. But there is a criteria for finding the stability of the equilibrium point that we will use here. If we assume the right hand side function of system 1, we define it as Fn, so Fn equal to Rn, and if we take the derivative of this Fn at the equilibrium point n equal to n star, and if this derivative is greater than 0, then we say that n equal to n star is unstable equilibrium point, unstable. and if this derivative is less than 0, then we say that n equal to n star is stable equilibrium point. So this criteria we are going to use. So if we take the derivative of this fn equal to rn, then f dash n star equal to 0 at the equilibrium point n star equal to 0. So this is r. So small r is the intrinsic growth rate. So if we take small r greater than 0, then this derivative is greater than 0. If we take small r less than 0, then this derivative is less than 0. So what we have here is, for if what is this small r? This is the intrinsic growth rate. So for the positive intrinsic growth rate, the n star equal to 0 is unstable, because whenever derivative at the equilibrium point is greater than 0, then n star is unstable. So for positive intrinsic growth rate, that means r greater than 0, n star equal to 0 of 1 is unstable equilibrium point. And in the second case, for negative intrinsic growth rate, that means r less than 0. So when r less than 0, then the first derivative of f at n star equal to 0 is less than 0. Hence by this criteria, n star equal to 0 of 1 is unstable equilibrium point. So that means in the second case, what you can say, that the disturbance that we are giving into the n star equal to 0, that decays out to 0, and in the first case, the disturbance that we give into n star equal to 0, that grows and grows, hence n star equal to 0 becomes unstable equilibrium point. Now we shall do the ecological interpretation of these results. Ecological interpretation of these two stability results of the equilibrium points. So first we have obtained unstable equilibrium point n star. When we obtain this we obtain in the case of r greater than 0. So you see, what was your solution of this exponential growth model? Nt equal to the initial value of n e power rt. Now if this r is greater than 0, then what is happening with the solution? Solution will grow and grow. So if you make the small disturbance into n star equal to 0, then the disturbance will grow as the time will pass out. So hence, what the observation we are getting, ecological observation, 0 population cannot persist. In this case, 0 population cannot persist. Okay, because as you will make sufficiently small disturbance into the population, then the population will grow, so it will not come back to the 0 population. Second is a small introduction of individuals into the population implies population increases. So this is the ecological sense of saying n star equal to 0 is unstable. And second point is stable equilibrium point n star equal to 0. What was the case? When r was less than 0. So in this case, when r is less than 0, then you see your solution. The solution always approaches to return back to n star equal to 0. So hence in this case, the population will because in this case when n star equal to 0 was what, rather saying stable, it was asymptotic stable, right? Asymptotic stable, because we are seeing that solution will come back to the 0, hence the population will eventually go extinct. Population will eventually go extinct. The second observation that we are getting for the asymptotic stability of n star equal to 0 is 0 act as attracting set, attracting point or attracting set, whatever you say. Why we are telling that 0, this n star equal to 0, this equilibrium point act as attracting set, attracting point, because whenever you are making a small or sufficiently small disturbance into n star equal to 0, then this disturbance decays out as the time passes out and your solution converges to the n star equal to 0. So in other way you can say that all the nearby phase points near to n star equal to 0 are attracted to the n star equal to 0, hence n star equal to 0 act as attracting point. And intuitively if you see, whatever result we are explaining here, this is true, because whenever in the first case, whenever the intrinsic growth rate is positive, then the population wants to grow because nt equal to n0 e raised power rt, exponential growth rate is there, and population moves away from the equilibrium point n star equal to 0. And in the second case, when n star equal to 0 is asymptotically stable, that means intrinsic growth rate is negative, then in this case the population always wants to shrink and it goes back to the 0 because nt equal to n0 e raised power rt. So this is what we wanted to discuss today about the equilibrium points, stability of the equilibrium points of the exponential growth model, population growth model, and we will stop this lecture here. In our next lecture we shall discuss about the real life scenario, a real life example in which the exponential growth model of single species fits well, and we shall also see the one uh, census data example, census of the US population, where the uh, our exponential growth model was used for the population prediction. And thank you so much for listening. Stay curious, keep learning different applications of mathematics to real world problems. Have a good time. See you next time.